Here's the job. On one processor core, it takes a full hour. So you buy a machine with 16 cores. 16 times the muscle. Surely 16 times faster? You'd expect that hour to collapse to under 4 minutes, a tiny sliver of the original. But you run it, and it finishes near 10 minutes. About 6 times faster. Not 16. And piling on more cores barely moves it. Something invisible is holding the whole thing back. This is parallel computing. The promise of many hands, and the stubborn limits on how much they can help. So here's the question for the whole film. If one core needs an hour, why can't 1,000 cores finish in a minute? Start with what we already know. One core runs one stream of instructions, strictly in order, one after another. The time it takes on that single core, call it T1, is our yardstick. Run it on n cores instead, and it finishes in time Tn. The speedup S is simply the old time over the new one. And how well each core is actually used? That's the speedup spread across the cores. The efficiency. So here's the dream. Double the cores, double the speed. A perfect diagonal, speedup equal to n. And here's what really happens. The curve starts to bend away almost immediately and flattens out. Why? Hold that thought. One line to carry forward. Speedup is the old time over the new, and that perfect diagonal almost never holds. Think of 4 painters and a long fence. The whole fence is the job. Each painter is a core. If just one painter works, they cover the whole fence alone. 12 seconds of work, while the other 3 stand idle. So put all 4 to work, each on their own quarter of the fence. Take a moment. How long does it take now? Quarter the work, quarter the time. 12 seconds becomes 3. All 4 cores busy at once. A clean 4 times faster. That's the whole promise of parallelism. In one picture. Work that divides cleanly, finishing in a fraction of the time. But that was the easy case. 4 equal pieces. Real work is lumpy, and lumps are where the trouble starts. Real tasks are all different sizes. Hand them out round robin, 1 to each core in turn, and look what happens. Core 1 is buried under 9 seconds of work. The others finish early and just sit there, idle, waiting. Because the job isn't done until the last core is done. Everyone waits for the slowest. That finish line is the makespan. 9. Same 7 tasks, same 3 cores. Can you do better than 9? Think it through. Pack them smarter. Biggest jobs first, each onto the emptiest core. The lanes even out. 9 drops to 7. And 7 is as good as it gets. 20 seconds of work across 3 cores can't beat 7. We're now limited only by the work itself. In real systems, idle cores don't wait politely. They steal unfinished work from the busy ones. That's dynamic balancing. This one too. You finish only as fast as your busiest core, so spread the work evenly. Now let's attack our own story. Suppose you do everything right. 2 cores, 2 completely separate counters, nothing shared. That should be a clean 2 times. Right? Core 1 bumps its counter, X. Core 2 bumps its own, Y. Different variables, they never touch. And yet, it barely speeds up at all. Sometimes it runs slower than 1 core. What on earth is going on? Here's the secret. Memory doesn't move 1 variable at a time. It moves a whole 64-byte cache line. And X and Y happen to live on the same one. So when Core 1 writes X, the entire line is dragged into its cache, and Core 2's copy is thrown out. Then Core 2 writes Y, and the line is yanked straight back. Watch. That's false sharing. The cores don't share data. They share a cache line. And the hardware pays the full price of sharing anyway. The fix is almost silly. Pad the 2 counters apart, so each sits on its own line. Now nothing bounces. Each core keeps its line to itself, and you get your clean speedup back. So go back to our first takeaway. The dream rarely holds. And now we know one more reason why. Even flawless parallel code can be quietly taxed by the cache beneath it. The law that explains it all. Take any program and split its time in 2. A serial part that simply must run in order, and a parallel part that can be shared out. On 1 core, the total time is just the 2 added together. Now hand it to n cores. The serial part can't be split. It stays. Only the parallel part divides by n. And the speedup is the old time over the new. That's Amdahl's law. 1 over the serial part plus the parallel part divided by n. Watch the 2 pictures move together. As I add cores, the parallel part shrinks, and the speedup climbs. 16 cores, 90% parallel. The curve says 6.4 times, not 16. There's the mystery from the very first scene. Solved. So here's a sharp one. 90% parallel, and you're handed infinitely many cores. What's the most speedup you can ever get? As m runs to infinity, the parallel part vanishes, and the speedup hits a hard ceiling. 1 over the serial fraction. A stubborn 10th left serial caps you at 10 times. Forever. That serial sliver is the whole story. To go faster, you don't need more cores. You need less serial work. Amdahl gave us our marching orders. To scale, drive the serial part toward 0. Unpatterned does exactly that. And it powers much of the modern web. Say you want to count every word across 1 billion documents. First, chop the pile into shards. Now the magic. Give each shard to its own core, and every core counts its own words. All at once, none of them talking to any other. This isn't barely parallel. Almost no serial part. Then comes the reduce. Merge the partial counts in pairs. Then pairs of pairs. A tree that collapses to a single answer in only log 2 steps. With 1,000 shards, the map runs fully in parallel, and the reduce finishes in just 10 steps. The serial part is a rounding error, so the speedup tracks the core count almost perfectly. So let's finally answer the question we opened with. When the work is shaped like this, nearly all parallel, 1,000 cores really do finish in minutes. The blowup was never about the cores. It was about the part that refused to divide. So here's the whole story in one breath. Many hands make light work, but only for the parts that actually split. The bit that won't divide, and the hidden cost of sharing, set a hard ceiling. So shape your problem to divide cleanly, and the cores finally pay off. 5 ideas, and they spell the word that says it all. Scale. Split the work across cores. That's the whole promise. But independent variables can collide on one cache line. Amdahl's law. The serial part is a hard ceiling. Balance the threads, or the slowest core sets the pace. And MapReduce keeps it embarrassingly parallel, so it scales. One last thought to carry with you. We assumed the job stays the same size, but what if, with 1,000 cores,